Hello, and welcome back to STEM Online Academy. All right. Uh, Today we're going to be looking at something very interesting. We're going to be looking at why the specific limit creates problems for a lot of students. Okay, even strong students. All right. So we're going to zoom in on this limit here. Okay. All right. So this guy right here. Okay. And when people look at this limit, the first mistake that they make is they input as x approaches 0 into the fraction. Okay. If you put in x approaches 0 into this guy, you are going to be wrong 100%, right? Because this will give you 0 over 0. You can't have that happen, right? Okay. You'll get an indeterminate form. That's what it's called. Okay. So that would be very problematic, right? So you do not put in x equals 0 into this function here and think that's the answer, right? Now, that being said, you should intuitively check to see if it is already indeterminate, right? So in your head, you should say as x approaches 0 into the function, right? That you can see that the entire thing, the numerator and denominator, are going 0 over 0, right? So that's fine because you have to first check to see if it's indeterminate. If it is, then you need to do some type of analysis on the function. Okay, so I'm going to go through that with you right now, actually. Right, so if you look at the limit, right, e x minus 1 minus x squared over 2 divided by x cubed. Okay, all right, so we want to evaluate this limit. It looks very tricky. So what we're going to do is I'm going to do this in a step-by-step approach. I'm going to use my technique for solving problems. And the first step in this technique is to visualize. Okay, you have to visualize the function and see the behavior of the function. Okay, now, first off, for step one in the visualization, okay, you'll notice that I made a graph of y equals e to the x. Okay, so if you look here, I have y equals e to the x. Okay, we zoom in on the graph here, y equals e to the x. Now, you can see that this is an exponential growth function, okay, because it's e to the x, all right? And what this shows us is as x approaches 0, right? Right. So as x approaches 0, so as x approaches 0, right? So that means going this way, right? You zoom in on that and see what I mean. As x approaches 0, right? Then you can see that the terms in our function become negative. Okay. There's a reason why I only graphed y equals e to the x, not the whole function, e to the x minus 1, blah, blah, blah. My point is to show that as if you have y equals e to the x, as x approaches 0, right, then we are getting closer and closer to negative terms in terms of x, as you can see the negative axis. Okay? Right, so that's what we have here. Right, so this is going to help us in how to evaluate this function. Okay? So, one way, one, sorry about that. One very useful way to analyze this limit is to notice that we can use Maclaurin. You know, you're thinking Maclaurin. Those of you who know Maclaurin, you should, if you're taking calculus, you better know Maclaurin. Otherwise, something is wrong. Okay, so Maclaurin, the Maclaurin expansion for e to the x. Okay, so e to the x is equal to the summation from n equals 0 to infinity of x to the n all over n factorial. That's the Maclaurin expansion for e to the x. Okay. Now, the reason why I'm going to do that, I'm going to explain in step 2. We're still in step 1. Okay. So we have this Maclaurin expansion. Okay. So we have this right here. Okay. As you can see with my summation, starting at n equals 0 to infinity, I plug in n equals 0. And we continue up in all the way up to infinity, right? Well, infinity, but you know what I mean, like da 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 da. Okay, so at n equals 0, we get 1. Okay, so I'm just right here. So in seconds, yeah, 1 here, 1, and then plus x, because x is 1 over 1 factorial, and then x squared over 2 factorial is x squared over 2, right? And then we add x3 over 3 factorial with x cubed over 6 plus dot, 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 dot. Okay, and you can see we got our expansion of e to the x. So the strategy here is very simple. Okay, the strategy here is the reason why we're using Maclaurin is to well, first off, I can substitute what e to the x is. I know that there's an algebraic expression for e to the x, and that expression is using the Maclaurin expansion. Okay. Number two is because the strategy is to subtract off the first few terms from our limit. Right. You'll notice that our limit right here, right? The Maclaurin expansions all the way up to x cubed over 6 factorial will survive, right? Except for everything before that, before the x cubed over 6 factorial, because we have that -1 minus x squared over 2. That will cancel. That will cancel the first 3 terms in our Maclaurin expansion. Okay, see what I mean? Okay, so that makes sense. All right. So now we're going on to step 2. Okay. So if you look at step, I need to zoom in on this guy a bit more. Sorry about that. Can you see it again? Yeah, there you go. Yeah. All right. So step 2 for the model, right? Step 2 is model. Okay. So our goal, as I say, is to cancel up to the first term. Okay. So looking at our limit. Okay. So let's rewrite our limit. As x approaches 0 of e to the x minus 1 minus x squared all over 2. Okay, that 2 factorial is 2. All over x cubed. That's what we want to evaluate. Okay, so the modeling part is just saying the framework of how we're approaching the limits. So you want to have your framework that you know is going to work, okay? Like a schematic, all right? And then write down the question, which I did. All right, and then we can move on to step 3, which is execute. Okay, on the execute phase. All right, that means actually substituting and putting things in. So since we know that e to the x, right, is 1 plus x squared over 2 plus x cubed over 6 plus dot 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 dot. I chose to go up to x cubed over 6 because I know where to stop here, right? Right. I want to stop on the first term that is not canceling. You understand? You'll notice that right here, right? You'll notice that right here. Just give me a moment. This cancels with this cancels with this cancels with this. So now it's just after substituting by Maclaurin expands for e to the x, there was a cancellation of the first couple of terms. Okay? So I'm just left with the limit as x approaches 0 of x cubed over 6 divided by x cubed. Okay? Now notice the x cubes will divide, and then I'm left with the limit as x approaches 0, 1 over 6, right? Of 1 over 6. Okay? So you can see that we got our answer. All right? Now, before we go to the last step, I do want to interject something about myself. Okay? Now, I know a lot of you who have trouble, who are in undergrad, right? May have trouble distinguishing how to deal with limits or whatever it is, when to use what. Things get trickier in university, no doubt about it. But I want to let you guys know that I was once in your situation. Not in university, but when I was in junior high school, there was a period of time where I had so much trouble with math that I thought I'd never improve. Okay? So much trouble. Until I met 2 teachers. Okay? And these teachers completely changed my life. They really did. Okay? They taught me how. This was in the end of grade 8. This was grade 9. I remember grade 9. Yeah, grade 9. they taught me a way how to approach mathematical problems. Okay, not specifically this technique. I came up with this technique, but they told me that you have to break the problem down into a system, right? Where everything's step by step, and you have to find what is working for you, how to problem solve correctly. Okay, all right. So from there on, in grade nine, still somewhat of a problem until mid to end of grade nine was the improvement because I I started to use I started to look back and think with the two teachers that I had in grade seven and eight, how to execute mathematical problems, especially when they're not algorithmic, they're not the same, right? The ones that are same that you can just mechanically solve are very easy, but I think you understand what I mean when they're not the same, especially on an exam. Your professor will put something that is not straightforward, not something that you can remember how to do from the homework, right? And that technique I came up with called the systems technique. Okay, as you can see here, step one is to visualize, right? All right. Step two is to model. Step three, okay, right? Step three is to execute. Sorry about the writing there. Okay. And then step four, where we're going to get to in a second, is to verify. Okay. This was a very logical system that I developed in high school. Okay. And starting from grade 10 and after, I just flew. I just flew in mathematics. Okay. So, and then university was great. I got like a 3.85 to 3.9 GPA in my double honors degree in mathematics and physics. Okay. So I want to share this system with you. I want to share it so that's why I can make the hardest math problems more, more, well, somewhat more attainable um, for those who are just entering university or who are in university. Okay, to set you up for success. Okay, so that's why this channel exists. That's why STEM Online exists. Right. Okay, so that's why I'm here, right? To support you guys in the very end, right? So let's move to verify, the verification phase, right? So the verification phase is here. I'm not going to necessarily write anything. I'm just pointing out step four. But verify means, right? In this case, we want to verify that our answer makes sense, right? Notice how we got the answer to be a positive value, 1 over 6, right? How do we know this makes sense? How do we know? How do we know that this ultimately makes sense? Well, we know it makes sense based on the graph. Okay? There's a reason why I made this graph in the first place. Okay? So let's look at the graph, right? Right? So, and that's why this method makes the most sense to do mathematics is because if you had just plugged in x equals 0, you would have gotten it wrong, right? Uh, if you had done, you can use L'Hopital's rule, but I didn't specify. I didn't say that you're allowed to use L'Hopital's rule here in the indeterminate form. But anyways, um, without the graph, you wouldn't know what to do. You wouldn't know what makes sense, right? Because right here, right, right. Once you make this graph, you'll notice the behavior, as I mentioned earlier, as x approaches 0, right? We start getting to the y-axis, and then after that, after we pass that, you'll notice we get negative values here, right? Negative, negative, all past x is 0. As you can see here, right? So that already tells you that our answer should be positive 1 over 6. Right? Because since we use the Maclaurin expansion and canceled out all the negative terms, right, and left with only the positive term x cubed over 6, right? That tells you that we have that our answer makes sense. Okay, so do you see how we can geometrically verify this problem in this case? You see what I mean? Right? It's a unique way of doing this problem, right? The way is using L'Hopital's rule if you wanted, but here I want to do it using my technique to show you how this can really help you with some somewhat unusual problems. Okay, so the point of this video is not to algebraically just substitute something in without blindly thinking, right? And I'm afraid in a lot of math classes, that's what they're getting you to do, to algorithmically chunk in a number into a formula. No, right? That doesn't, you need a system in order to do mathematics correctly. Okay? All right. So that was the verification phase. Right. So that is it. That is it for today's video. Now, for those of you who have noticed that I've probably been doing like one video a week, been very busy. I'm going to try and do two next week. Okay, I'm going to go back to two, see how that works. I just have to shuffle things around. All right, so we'll be back to two videos. Stay tuned. Things are going to get very interesting. I talk about a lot of different interesting problems when it comes to calculus and physics, physics courses, and I say analysis less calculus and physics courses, right? Okay. So if today's video helped, like and subscribe. I really appreciate it. If you can join the channel, it'd be great. STEM Online wants to be able to make, we want to make mathematics great again. I feel like lately mathematics doesn't get always a positive name, but my job is to make mathematics great again. Another thing, if you had trouble understanding the video or my systems, something about the systems technique, you want some more info, there will be a link in a free link in the description below. It's completely free. It should be a PDF. Sometimes the link acts weird. I'm going to try and make it work. Hopefully it works. Okay. So there's going to be a free link on that. Now, if you understand the technique or you don't understand it, if it's both, then you may want to look at another resource, okay? And that is, especially if you don't have the foundations of how to do mathematics creatively and logically, you may want to look at my resource Axioms. It's my new book, okay? And it's going to help you. It's pretty much an introductory book to logic, a rigorous introductory book to logic, which will help you understand the rules of mathematics, the axioms of mathematics, everything you need to know about how to start out, the foundations, pretty much. Okay, mathematical foundations, right? Which will help you. Actually, will give you extremely solid foundation once you to move into something like analysis plus calculus. Today is calculus. We're just mainly doing calculus today, but I hope you understand what I mean. It will help you have a very comprehensive understanding of these topics, right? Okay. So there'll be more new videos uh coming up, and yes, a lot of interesting topics. So stay tuned. I hope to see more of you guys. And yes, things are going to be very interesting. All right. Have a great one, guys. Have a great week. Bye bye.